Hey everyone, and I guess let's just get something back. Can everyone hear me properly? Can you hear me?
Yeah, we can hear you.
Yeah,
Hello,
we
guys.
can hear you. We can hear you.
All right, all right, I guess we'll get started then. So, hey everyone, I am Omar from Google's Developer Student Club, McMaster University. I'm one of the workshops and talks co-leads for the club, and today I'll be presenting to you the practical applications of mathematics in computer science. And I know that sounds like it's straight out of a textbook, but bear with me. Hopefully, you'll learn something interesting today. And I will start sharing my screen with you guys. I hope, oops, that's the wrong screen. I hope everybody can see my screen. All right. So, the topics that we're going to cover today. So, this is going to be a workshop where I basically write down and there's no slides. So, hopefully, you'll enjoy this way more than just reading PowerPoint slides, and it will be a break from coding today because we're not going to get you to code right now. So, topics to cover. These are the topics that we're going to cover today. We're going to start with matrices, and then we'll go to computer graphics, and then from there, we'll branch off into computer vision, and then finally, if time permits, we'll talk about PID control loops. All right. So let's start off with good old matrices. If you're in engineering one or computer science folks have already taken linear algebra, so they know what matrices are. But let's just do a short refresher. Anyways, so matrices. So let's start with the one that most people are familiar with. It looks like a grid, essentially. So think about it like a chessboard, right? We're not going to draw an entire chessboard here. Let's just draw a grid, right? You have rows, you have columns. Some people like to think of this as an Excel spreadsheet that basically everybody is familiar with. And the notation for size that we use here. So you have 1, 2, 3, 4 rows, and 1, 2, 3, 4, 5 columns. So the way we write down the size of this is rows multiplied by columns. So in this case, it would be 4 by 5. And the amount of entries you can store inside a matrix is just multiplying these two numbers. In this matrix specifically, you could store 20, and you could have one-dimensional. We call them one. They're really just a special case of two-dimensional. So you could have a column matrix, which basically looks like a column. You could have 0, 1, 2, and this one it would be 3 rows times 1 column. And you could also have a row matrix, which is just looks like a row essentially. And this one has 1 row multiplied by 3 columns. And in both instances, you could store 3 entries in here. So we've handled the 2D case, and I guess this is also 2D, but a special version of the 2D case. Let's talk about a 3D matrix. Sure, most people haven't seen this one before. So a 3D matrix. So what is a 3D matrix? What would it look like? So I have a picture here that I will just paste into our notes here. So this is essentially what a 3D array looks like. So in the 2D variants of the array, we have cells. So these are essentially cells. But when you step it up to a 3D matrix, what you get is that each entry in the matrix is a cube. As you can see here, this entire cube holds one entry, which is true, and we just labeled it on all sides just to represent that it is in fact the same entry, right? So to get the amount of entries that you could store in here, you just multiply the dimensions again. So in this case, you have a height of 4, you have a width of 3, and a length of 2. And there's different ways which one's the width, which one's the length. That doesn't really matter. In the end, it's all the same. And in this matrix specifically, you could store 24 entries. And the best place you have seen this used is Minecraft. So think of Minecraft in this scenario, right? Think of Minecraft. And just to help you think about Minecraft, I will paste an image of Minecraft. All right. So in Minecraft, they don't exactly store everything using a 3D matrix, but chunks are sometimes stored using 3D matrices. And you can see why this works out really well, because every block in Minecraft can be represented by one cube inside a 3D array, right? So in this case, if a chunk is 8 by 8, it would be an 8 by 8 by 8 3D array. And what they do is they would basically, inside each 3D array, they would give each block a number. So a grass block would be, in this case, whatever number it would be, let's just say 20. So they would basically label each box inside the 3D array with a specific number. And when you look at it, when the game is rendered, it would end up looking like a grass block or a wood block or a leaf block or an air block. An air block is also a thing in Minecraft where when there's nothing there, it's filled up by an air block. Right, so that's one of the cool representations and uses of 3D arrays, things like Minecraft. And that's what we call this type of data is usually called voxel data. And I'm not particularly sure why they call it that, but that's what they call it. Things like games like Minecraft are called voxel games. So we have that, all right? So that's matrices essentially. And that's I guess your first application is Minecraft. All right. So let's move on to computer graphics. So most people in this call, most people in this session probably have a 1080p monitor. You might have a more expensive monitor, but most people have a 1080p monitor, which has a resolution of 1920 by 1080, right? And if you were to visualize that, we're not going to draw that many rows and columns, right? So all that means, actually, let's just try to make it more visually accurate. It's, it's more like this. What that means is that you have 1920 rows, 1920 rows, and you have 1,180 columns. You could essentially think of it as a matrix because each monitor actually has pixels, small discrete parts of the monitor. If you look in very close to your monitor, you will see that there's small squares inside there. And since we can't draw all of those, we'll consider the simpler case. We'll draw a beautiful 4 by 6 monitor, which has a resolution of 24p, 24 pixels. Isn't that exciting? So the idea I'm trying to bring home is that a monitor or basically any image can be rep can be represented by a 2D matrix. And how do we do this? How do we represent 2D matrices in memory? So most computers these days have a thing called a GPU or a graphics card, which is notoriously hard to get by these days. And what GPUs do is they store these things called textures. And I'm sure if you're into video games, you probably heard that term many times before. You've probably seen that term in your video game settings. So GPU stores textures, which is essentially a 2D matrix in essence. And the reason we need a GPU and we can't just use your CPU to render everything is because the GPU is actually it has much more specialized data structures inside of it. So it's very good at doing things like matrix math. Because of the way the circuitry is specifically designed to do things like matrix math and basically any operation that involves matrices. So that could be matrix multiplication, addition, things like dot product, if you've seen that before. So as you can see here in our image over here, right, each pixel can represent any color that you could think of. So each pixel has an RGB value. Some of you might have heard that before as well. So let's try to talk about the RGB values. So each pixel is made up of R, G, and B, right? A lot of folks are familiar with that as well. And these are what we call subpixels. All right. And each value, so R, G, and B, each subpixel has its own individual value, which can go from 0 to 255. All of them go from 0 to 255. And what the numbers here represent is that if you had a the way we represent colors oftentimes is using an RGB, a column, a row vector with RGB in there, right? And each of these goes, like I said, from 0 to 255, all right? And what 0 to 255 represents is the intensity. So if the value of R, let's say, is 0 inside a pixel, that means there's absolutely no red color in there. But if the value of R is 255, you have the maximum amount of red you could have. And you could essentially combine all of these colors with specific combinations to generate almost any color you can think of. And I believe the number is like 16.8 million for RGB. And the reason it goes from 0 to 255, this isn't a special number. The reason we use 0 to 255 is because memory, each subpixel is stored in 1 byte. So 1 byte has 8 bits. All right. And 8 bits can only store from 0 to 255 because of the amount of bits you have in there. If you flick them on and off, the maximum number you can generate using those bits is 255. So that's why the maximum number, the maximum value of RGB is 0 to 255. All right. So now that we have that information, we can reason that for RGB, each each subpixel takes up exactly 1 byte in memory. So memory could be RAM, it could be your hard drive, it could be any sort of memory. So that means that 1 pixel by itself, so these are subpixel, right? And 1 pixel would be this entire thing, RGB, right? So that means 1 pixel takes up 3 bytes in memory. All right. Does this all make sense so far? Do we have any questions about anything we've talked about so far? All right, that's cool. So we'll move on. So what we actually do is instead inside the GPU or like any storage mechanism, what we do is we actually store this using 4 bytes. And the reason for that is like computers like working in powers of 2, right? because we use binary in computers, everything wants to work with powers of 2. So just for memory alignment and for that kind of stuff, we just use 4 bytes because 4 is 2 squared. The next number up you would want to use is 8, and then it goes to 16, 32, 64, 128, and it goes up from there, right? And what I'll do is I will paste a color wheel here. If you've used graphics applications before, you've probably seen something very similar in that application. This one specifically is from paint.net. And as you can see here, if we combine the values of RGB to their maximum intensity, what we get is white. Once you combine all of those to their maximum intensity, you get the color white. And if you start like moving these sliders around, you move around in the color wheel. And the color wheel is actually a projection, if I believe it is a 3-dimensional or a 4-dimensional surface onto, if you actually try to if you try to visualize the color wheel as it's actually supposed to be, it's actually, I believe it is in 3 dimensions. That's where it works out. So you move these sliders around and you can basically get any color in the color wheel. That makes sense so far? All right, so what we've talked about so far pertains to the field of math called linear algebra. If you're in engineering, you're going to be doing this right now. If you're in computer science, you've already done this. If you're in first year, I guess everyone above has done this as well. If you're in high school, you'll probably touch upon this in university as well. All right, so now that we have linear algebra down, let's bring calculus into the mix. All right, let's talk about calculus. And usually we start off calculus with the notion of a derivative. All right, and the derivative, most folks have probably know what this is by now, is the rate of change of a function over an interval. Right, that's what a derivative is, and I will paste a nice image for that. This is essentially what the derivative represents. It's the rate of change in y divided by the change in x, and as delta x approaches 0, you get the derivative function. All right, and it basically measures how fast the function is changing. And you can get the equation of a tangent line. It looks like that. Like tangent lines to the function look like that. So why does a derivative matter in computer science? So what we're going to talk about next is computer vision. Now that we've touched upon computer graphics, it should make a little more sense. So how does this apply to computer vision? How could we use this? How does this apply to computer vision? How could we use this? So let's just say, for example, I gave you this nice Pepsi logo, all right? This is what it looks like now. And I told you to write an algorithm that figures out what the edges in this image are, all right? So what are the edges in this image? Let's just draw it out for our own reference so we know what we mean by edges. It's basically the outline in the image. So how do you write an algorithm to find the outlines in an image, right? So that's one outline, right? And of course, Alexa, sorry, let me just mute the mic on Alexa. All right. Another outline would be the circle, right? It's not perfectly aligned, but I hope we all get the idea. It's the circle, right? And that's one of the other outlines, right? So one of the very useful applications of derivatives in computer vision is edge detection and motion detection. So if you've got one of those fancy motion cameras that you've installed right outside your house, they also use similar algorithms that we're going to talk about. So performing edge detection and motion detection. All right, so let's take this. Take this logo. All right. So as we talked about before, each pixel in this logo, every image is represented by a 2D array, 2D matrix which has pixels inside it, right? So each pixel in this image is made up of RGB values, right? So we start off by finding the derivative function of the RGB values. But as I talked about before, RGB, the color space itself that represents RGB, is actually a higher dimensional function, and taking derivatives in very higher dimensions, we can't visualize that, and it's very computationally intensive. So what do we do? What do we do? Let's make this problem simpler for ourselves. All right? Let's make the problem simpler. And how do we do that? Well, one of the easiest cheats that we usually do is just to convert the image to grayscale. So we convert the image to grayscale. And that's essentially what most people refer to as black and white, right? So I will paste an image of the Pepsi logo in grayscale. And as you can see, all of the edges in this image are still preserved, right? There's no loss of edges. All of the edges are still here. You could still differentiate between them very well. And if you try to map them out into the RGB image, it would still map out just fine. And what's the difference between RGB and grayscale now? So instead of three different values RGB, each pixel in grayscale is represented by just one number, by one number. All right, and that would be the G value, which doesn't stand for green in this case. It stands for gray, right? And this also goes from 0 to 255, just like any other value. And what this grayscale image is basically an image with different shades of gray. So you don't need all the RGB values. All you need is different intensities of gray, right? And as we said before, the edges are still preserved, right? The edges are still preserved in this image. So now we can take a much easier derivative. All right. So step 2, take the derivative. All right. So now what we can do is, instead of a very higher dimensional function like RGB, which goes beyond 3 dimensions, we can represent this image, the image, and I'll show you a nice graph in a second. The image can be represented by a 3D function. And what does a 3D function look like? What does it look like? I'll paste another image. There we go. So that's what a 3D function looks like. And if you haven't seen them before, they're beautiful. Actually, one of the great examples of this is actually Pringles. Your Pringles are model 3D functions that a machine uses to slice chip slices, essentially. And this is an example of a 3D function. example 3D function. So usually traditionally functions are like this, where you have x, you have y, and you have some function. But in this case, x and y, so this is a 2D function. But in this case, x and y are input, and the output value is z. It takes in two input values instead of one in a 2D function, and it outputs a third value, which you can map into the third dimension. So what does that look like for us? What does that look like for us? So we'll also have three axes. We'll have our y, we'll have our x, and our z value is the gray value, which is essentially, if this is 0, up here somewhere it's 255, right? And it's not very easy to draw this out, but you can imagine that each pixel is down here. All of these rectangles are pixels, right? You could map out the entire 2D plane with pixels. And what you would get is if you look at it from top down, each pixel will have a number from 0 to 255, right? So that's how it would look like. And unfortunately, you can't. It's not very easy to draw it out. So hopefully you can imagine that. So you fill each of these boxes with a number: 120, 0, 25, 63, any random number, and just imagine that number coming out as a bar graph, that box just extruding from the plane and mapping out onto the z-axis, which is our gray value. All right. And if that if it's still hard if it's still hard to visualize, then that's perfectly fine. It's nothing to worry about. So now that we've talked a lot about that, let's take a look at our nice grayscale image again, right? So what we do is we take sample points, all right? We take sample points. So let's take a sample point along one of the edges. Let's call this P1, all right? And if we zoom in, let's zoom in into that area, P1 over there, this is what it looks like, right? And it's very pixelated, and that's great because these calculations work on individual pixels, all right? So what we can do is we can take a sample point, right? Let's take a sample point along this edge. And what we do is we try to measure the change in colors in every direction, essentially, all right? So you would measure, so the length of the arrow that I draw here represents the size of the derivative. Let me just zoom in a little bit over here. All right, so the length of the arrow that I draw represents the value or how high the derivative is. So in this case, if you go from here, if you go from this value to this value, there's not that much of a difference. It's almost the same color. But if you go from this value and you draw a derivative in this direction, the value is very high because the value of the pixel actually changes quite a bit because it goes from almost black, gray to immediately changes to white. So your derivative value is much higher, right? Your derivative value is much higher in these directions, but it's much smaller in this direction because the colors are very, very similar, right? And what you can do is you can perform the same calculation across all of these points, right? You can perform the same calculation. That's supposed to be a little smaller, right? And once you do that, right, let's just assume you perform that calculation across all of these points. And in the actual image, you would do this calculation for every single pixel. We're not just choosing these randomly, but just for this example's sake, just so we can go faster, I'm choosing points across the edge, but when the actual algorithm runs, it runs across the entire image. All right. So when the algorithm runs, it labels points with high derivatives. All right. It labels points with high derivative values attached to them. right? So these are the points where you would find high derivative values. Inside here, if you were to sample inside here, the colors are the same all around, so derivative is 0. Same over here, derivative is 0. Same outside, the color is the same in every direction, so the derivative value should be 0. All right. And now what happens is that you can basically trace across all of these points. All right. You can trace across all of these points and you'll get an edge. And if you apply this methodology to the entire picture, right, what you do is you get a, well, what we call this is a gradient intensity function. So a gradient is a derivative in multiple dimensions. And the reason we can take derivatives multiple directions, so if you look at the 2D function over here, you can only take derivatives you either go left or you go right. But in a 3D scenario, you can go in any direction. You can go in this direction, you can go in that direction, you can go in that direction. There's infinitely many directions you can go in. But usually we pick, so a pixel looks like this, right? So let's just assume that these were all pixels, right? And this is our sample point, right in the center. We would basically be measuring the derivative across these pixels. All right? That makes sense so far to everybody? Any questions about this? All right. I guess so I will actually show you what this looks like. So I have a Python script over here, and this is using a very, very popular computer vision library called OpenCV. And essentially what we're doing here is we're reading in the image, which is a flower, all right? And we're taking away noise, and if you've ever watched a YouTube video, you've probably seen random artifacts and stuff like that, different color degradations and things like that. We try to take those away as much as possible. And then what we do is we convert the image to grayscale. So this function essentially is CVT color, convert color. It says color BGR, which is a different way of saying RGB, to gray. And then we run the edge detection function. And this algorithm is called canny edge detection. That's one. There's many edge detection algorithms out there, but they all have a similar idea behind them. You measure change in pixel intensities, all right? And let's run this, all right? So here's the original image, all right? This is the image that we inputted into the algorithm, and this is the output we got. And as you can see here, every time there's a sharp change in the color, right? Every time there's a sharp change in the color, there's an edge. And sometimes that sharp change isn't sharp enough. Like you can see here, the change here isn't really reflected over here. Some of these circles in the background do change enough for it to detect it, and they show up here. But even then, they don't show perfectly, which is why this isn't the most perfect algorithm out there, and requires a lot of fine tuning for it to work really well. All right, so that's edge detection. All right, any questions? Any questions about this? We'll go back to our OneNote. Any questions about anything we've said so far? All right, I guess not. So now we're going to move into something that's much more intense, and it's perfectly fine if you don't understand everything in here. So this is a very useful application of calculus. We call them PID control loops. All right, the name is an acronym in of itself. So PID stands for proportional integral. Right, so that's what the P stands for. The I and the D stands for derivative. Cool. So we've introduced a derivative before. Let's just do a short primer on integrals. So I will paste another image. All right. So an integral is basically the measurement of the area under the function's curve. All right. Or it's also considered the summation of the value of the function on a specific interval. As you can see here, we try to estimate the area under the curve, between the curve and the axis using rectangles. Right, that's one of the ways we look at it. And the notation for this is usually from a to b. These are x values. We take the integral. This is the integral symbol. This is the integral symbol. Right, we take the sum from a to b of f at x with small changes in x, which is dx. All right, hopefully a lot of people remember this from calculus class. And now we're going to introduce some terminology that we're going to use for the next 20 minutes or so. So to understand PID controllers, we have a process value. So just to give a short introduction, PID controllers are used to control systems essentially. Systems such as thermostats or your car or an aircraft. All right. So the process value, we're going to shorten this to PV, is the system that you're trying to control its current state. So current state. So in case of, let's just say, current state of the system. All right. If you had a thermostat and the system was the temperature of your home, in this case, it would be the current temperature in your home, right? The current temperature in your room. That's the process value if you were trying to model a thermostat system. All right. And the set point, this is also called the desired value. We're going to shorten this to SP, is the desired state of the system. Cool. So like I said, this would be the temperature you would want your room to be at. So if your room is at 18 degrees right now, which would be your process value, and you want to set it to 22, 22 would be your set point. All right. And we have another term called the error value. And we use E to shorten this. And this is essentially the difference between the set point, SP, and PV, your process value. So if you want your room to be at 22 degrees, but it is currently at 18, the error in that case would be 4. And up here, we mentioned proportional. And what proportional is, it's essentially another way, proportional is another way of saying error value. It's the same thing. It's the difference between the set point and the process value. All right. So now that we have all of this defined, we can come up with a very nice equation called the PID loop equation. All right, now I'm going to drop an image in here, and it's going to look pretty complicated, but we're going to try to work through it. All right, so this is a PID loop equation. All right, you have your error, right? You have the error, you have the integral, you have the derivative. All right, and in this case, KP, you can see there's KP over here, there's KI, and there's KD. All right, KP, KI, and KD equal card caps flashbacks. Yep, that sounds about right, Amit. All right, so these are essentially what we call tuning constants, and these are going to make more sense when we're through the entire system. And what a PID system does, it essentially, if you were to draw a nice block diagram, it will take in your process value and it would also take in the value that you want, which is your set point, all right? And it would take in, it would put it through the PID loop equation, right? It would do some calculations on that, and it would tell the system what to do, right? Here is the output that it produces. In this case, we have it labeled as U, so we're just going to use U over here. And essentially what it does is it takes the current state of the system, right? And it takes in the value that you want the system to be at. It does some calculations, and it outputs a command, right? It outputs the command. It takes the next. It sees how the system changed. It takes that new state of the system in that changed based on the command it issued before. It does it again, and it keeps doing that till your set point and your process value have an error of essentially zero. All right, that's the basis of PID controllers. And before we talk about how it works, how this entire daunting at first sight equation works. All right, so what are some uses for it? Thermostats, we've used that example. So thermostats use this. All right, cars, eco car caps flashbacks, like someone mentioned. Cruise control, right? Cruise control is a system that controls the speed of your car, right? And autopilot. This is not the Tesla autopilot. This is real autopilot that's used in aircrafts. Okay, so your airplane usually has an autopilot system, and they get progressively harder as you go down the list to implement. So obviously, we're going to talk about autopilot and aircrafts. All right, so let's try to design an airplane. Let's say you're an engineer at Boeing or some other aircraft company, Airbus. You were tasked with implementing an autopilot that does airplane speed control. Cool. So in this case, let's just redefine our terms. So set point, SP, would be the desired speed. And process value, PV, would be your current speed. All right. And we're going to start with the proportional term over here because that's the first term. We're going to start with that. All right. So the proportional error, remember these are the same thing as we mentioned over here. All right. So proportional error would be, let's just say you want your airplane, so you want your airplane to be going at 300 kilometers per hour. Airplanes are fast. And your current speed process value is 210 kilometers per hour. All right. So your error in this case would be 300 minus 210. All right. And you get an answer of 90. And what you do is you multiply this by KP. Now, KP is an arbitrary, we shouldn't say arbitrary, but in this case, it is pretty arbitrary. Arbitrary value, which could be any decimal or integer number, could be anything. All right. And that's what the KP is there for, right? And just to hit that point home, it looks exactly like kp.e. In this case, this is your E, and this is your KP. All right. This is what the image looked like. All right. So what we could do is you could say, hey, there's an error of 90. So let's just push our throttle, or a more analogous example is in your car, you would floor the pedal to 90% of its maximum value. All right. So let's try to graph out what happens when you apply 90% throttle to an aircraft. All right, let's just try to graph that out real quick. So you would have a 2D graph with x-axis is time, and your y-axis would be speed, right? And we are going to say that this value over here is 210, and this is 300. All right, so this is time 0, and down here would be time t1. Time t1 represents when you change the set point from 210 to 300. Okay, that's when you change the system. So before t1, you're cruising along at 210 kilometers an hour. All right, you're doing just fine. Suddenly, you want to change to 300 kilometers per hour for whatever reason, right? This is 300 kilometers. This is 300 kilometers per hour line. Your PID system sees an error of 90 suddenly. If before it was 0, right? Your error was 0 before. Now suddenly sees an error of 90, and it outputs a command says because of what we have here, it outputs 90% throttle. So your aircraft suddenly starts increasing in speed. But the closer you get to your set point, this error value decreases. So the amount of throttle it's asking you to apply to the system decreases with time. So what happens is that you start reaching your set point, but eventually you actually start decreasing because you're not applying enough throttle anymore, right? And then after you drop a bit, your error value starts going up, so it applies more throttle, right? But the problem is doing this only, you will never reach 300 because your error value will keep on decreasing and the amount of force you keep applying to the system also decreases with that. So you'll basically never reach 300. So how do we deal with this problem? What we do is we introduce we introduce the integral. All right, and in this case it would be ki times, since we start at t1, right? So t1, t1, all right, these are the same t1s. The t, whatever time you're looking at the moment, the error value, right? You take the integral of the error value. So let's look at what the error function would look like. I have a graph that's already made for this, just to save some time. So here's what the error graph would look like essentially. All right. So at t1 before, your error value is 0, right? And suddenly at t1, you set the autopilot to 300 kilometers an hour, and suddenly your error function just suddenly goes up all the way to 90. And as your proportional controller is telling it to 90% throttle, 80% throttle, 70, 60, 50, it starts going down. But what happens is that your error function decreases with time, but then it will go up, right? It will start going up again, and it will come down again, all right? And the integral in this case is the area of everything that's underneath the curve beneath the curve and the t-axis, the x-axis. That's the integral value that you're seeing here. All right, and what this does is that it keeps track essentially of how much error you've had in the past. And when this proportional value starts going down, because this system remembers that you were very far away, because of how high the integral value is at this point, it remembers that you were way far away from the error before, and to compensate for that, it will give you an extra kick near the end. So you will actually end up reaching 300 kilometers an hour, right? So let's try to graph out what happens when you combine a proportional and integral controller. When you add up the proportional and integral terms. All right, so in this case, this is how far we've got. So U is equal to Kp dot E, which is from up here, right? That's Kp dot E. We've talked about that, plus Ki times the integral from T1 to T of the error function. Oops. And that's this term over here, right? So if we try, so what happens? What happens when you combine these two? What happens? I have another graph that shows that. What happens is that, yes, you do reach 300 kilometers an hour, but the bad part about this is that you actually end up overshooting 300 kilometers an hour because of how much accumulation you had beforehand. You go over the top, and then suddenly your system goes over 300 kilometers an hour, and then it sees, oh shoot, I'm over 300 kilometers an hour. I need to come down, and then it goes below the set point, and then it sees that it's below the set point. It goes above, down, up, down, and it keeps oscillating like that. All right. So we don't want this. In some cases, it's fine, right? In some cases, you might not care. But for aircrafts, you really want to deal with the situation. So how do we deal with this? How do we deal with oscillations? And that's where the final piece of the puzzle comes in, the derivative term. The derivative. And that's kd times the derivative with respect to time of the error. How much is your error changing per second, essentially, in this case? All right, and that's the final term in our equation. All right, so let's try to graph out the error function with the proportional and integral terms combined. So the proportional and integral terms combined, what we would get is something like this, right? So these are the oscillations. They match up with the oscillations up here. The oscillations are also represented in the error function. And when you go above your set point, the error function becomes negative. All right. When you're below the set point, your error function is positive. And the reason for this is if your set point is 300 and your process value is, let's just say 315, SP minus PV is going to be negative 15. All right. Does this make sense so far? Do you have any questions about this? All right. So what we can do is we can take the value of the derivative. All right. So these orange lines basically represent the derivative. They're almost tangent lines. So from here to here, the value is positive. All right. And then somewhere, let's just see the brighter color. Somewhere over here, the value goes down to 0. All right. The derivative at this point would be 0. That's a tangent line. It has a slope of 0. And what happens is that when your system starts to oscillate like this, like over here after T2, that's when your oscillations start. The derivative is actually pointing in the opposite direction, right? When your error function, when you're above the set point, your derivative function is actually negative, all right? So what happens is when we combine all of these terms together, since the derivative is acting in the opposite direction, right? What we can do is, over time, it cancels out the oscillations completely. And what happens is that your system eventually it either ends up achieving your set point or it gets really close to the point where it's like 299.995 or something like that. All right. And that's, if you have any questions about that, you could leave them in the chat and I'll be happy to answer. That's all the content for this workshop. And I understand that the PID stuff at the end is a lot to take in. There's many good resources if you Google these terms. So just in summary, today we talked about matrices, computer graphics, computer vision, and PID control loops. And that's it for the workshop. If you have any questions, I'd be glad to answer. And we'll be sticking around till 9 o'clock in the chat just to answer your questions. And I'll also be on the Delta Hacks Discord over here to answer any questions, or if you just want to talk about anything we went over right now, I'd be happy to talk about it. And that's it. Thanks for attending, folks. No problem. It's my pleasure. I love talking about this stuff. I'm glad to hear that, Amin. There we go. Raffle code for this workshop is math. You're welcome. Yep, thank you everybody for attending this workshop. I understand it's late at night, and I believe the next event is the game night, so the games night. So hopefully you guys will have a nice de-stressor after this. Yeah. What is my program of study? Oh, I'm in software engineering, but I'm also doing a math minor as well. So there's that. I try to enjoy it. Sometimes there's things in math that aren't so nice. Discrete math is probably one of those, which is useful, but yeah, yeah, discrete math is like the demon in mathematics. And very fortunately, we happen to have 2 courses for that in McMaster. So the first course is called Software, and let me see if I can pull it up real quick. Software Engineering, BM3. So this is the first course, Software Engineering 2DM3, Discrete Math with Applications 1. In second year, this is in your first semester. And the second semester course, which is an extension of this, is called Software Engineering 2FA3, which is Discrete Math and Applications 2. And I am doing this course right now. I already finished 2DM3. I'm doing 2FA3 at the moment. It seems to be a lot more excruciatingly painful than 2DM3, if I'm being honest. Yeah, that's the discrete math courses at McMaster. And I wasn't able to explain everything around all the things that we talked about. So hopefully, if you're interested, if any of this interested you, you will. There's a lot of resources that you could use. There's Google. There's entire courses you can do on these things, just on computer vision. So I guess if you guys have any questions, I'll be in the Discord. And thank you for coming out and won the session right here. Thank you, everybody. Oh yeah, plugs for DSC. We do have a Discord server, which I can send an invite to. So we're affiliated with Google, and we do a lot of things. We have workshops. Obviously, this is one of the workshops we hosted. Just yesterday, we hosted a workshop on Unity game development. Right. So if you guys want to know more about it, you can join the server and ask questions. There's many different teams. There's outreach. There's external relations. There's marketing and branding. There's community and code. There's many
Workshops
things
and
that we do.
talks.
There's
More
also web
team.
development if you're into that stuff. A lot of that's happening in this hackathon, it seems, with React and stuff like that. So if you're interested in stuff like that, we also have a team for web development. If you want to learn, it's a great place to learn.
Applications are out
Yep.
right now too, if you're interested in joining a team. So check out the Discord and get in contact with
I'm
one of
not
the
sure
leads.
why, but the audio comes through my speakers instead of my headphones for some reason. I'm not sure why.
That's weird for you right now, or
Could you say that again?
like the audio's coming through your head, like
Yeah, the
your.
audio my computer audio, like
Oh,
Hoppin is coming through my speakers instead
it's
of my
probably
headphones.
defaulting to your speakers instead.
Probably. That's fine.
Yeah. Hey
All right,
guys,
I
join the
guess.
Discord. We do have a couple workshops upcoming. The next one is going to be Intro to Algorithmic Investing if you're interested in finance and technology. So make sure to sign up for that one. I'll drop that link right now if anyone's interested. Do you have the link with you, Omar? I'm trying to find it right now.
Sure, let me just find it real quick. Here's the link to our next workshop. It's going to be happening Friday, January 21st. Algorithmic investing. And we do lead code nights regularly. So the next one is January 19th. This is done regularly by the community and code team. So if you're interested in learning about lead code and just need a mentor or something like that, feel free to join in on that.
Yep. All right. Thank you guys for attending. See you guys later.
Yep. See you guys. Good night.